Okay.
Okay. Udah, mulai.
Dah.
Good evening, everyone. Today we'll be presenting our aircraft design. We are from Group 13, and we are creating an unmanned piston-propeller cargo aircraft. With me are, there's myself, Raihan Daffa Muhammad, 112. There's Fahmi Faisal Habib, 115. Bayu Dimas Febriansyah, 121, and Gregorius Aginta Gintings, 122. All a part of Group 13. So our design comes from the design requirements and objectives that were given to us during the initial stages of class. So the design requirements first, we're generally making an unmanned cargo piston propeller aircraft, which to make maximum takeoff weight must not exceed 4,000 kilograms. Its design is according to its unmanned nature, with a cabin volume that should not be less than 9 meter cubed and a maximum payload which should not be less than 1,000 kilograms. It's planned to be certified by 2026, certified with CASR 23 and 36 as its airworthiness regulation. And on the right side of the screen, you can see several criteria for its flight performance. There's some with a range, there's a maximum service ceiling, there's a takeoff and landing distance, and a maximum rate of climb. And for a multi-engine aircraft, it must comply with the one engine inoperative requirement from CASR 2367. However, it's worth noting that the aircraft that we've designed consists of one engine only. So for that criteria, it doesn't really apply in our case. So this is the mission profile, or at least one of the options. And so it would start to climb as soon as takeoff until it reaches 10,000 feet, and it will cruise for 250 kilometers, at which point somewhere in the middle it will start to do a step climb for a minute at 2,000 FPM, and it will then cruise again at 12,000 feet at 250 kilometers per hour, and it will start to descend at 1,600 FPM and climb again at 1,600 FPM until it will cruise at 5,000 feet, 250 kilometers per hour for around 100 miles until it descends and lands at the landing zone. So next, these are our competitor analyses. There is about 8, and these competitors are to gauge our ideas of how our airplane is supposed to be with the reality of how airplanes are, so as to not make our designs way too absurd or unrealistic. However, it's worth noting that we are making an unmanned cargo aircraft, but the ones that you see in the screen before you are all passenger airplanes and also manned planes. There is no cargo UAV yet available on the market, so our job here essentially is to turn one of these passenger airplanes into an unmanned cargo airplane, and the steps to do which will be explained shortly. These are the diagrams for the competitors, and maybe for ours there won't be any windows because there are no passengers, but this is just for your information. And for the aircraft configuration concept, Bayu can take over for me. Hello, Bayu.
Okay, for the aircraft configuration and concept, the initial configuration of our aircraft is a monoplane aircraft with an unswept wing and a low wing location. It uses a conventional wing HTP and VTP. The wing is also cantilever. We will try to apply the use of winglet and a sharp tip. On the empennage is conventional with a fixed horizontal tailplane. The engine is tractor, which means that it's in the front, and it is also nose mounted. The landing gear is tricycle and fixed. The fuselage is also rounded with a rectangular cross section. The weight estimation of our aircraft is calculated using Roscom strength. After calculation, we decides that the takeoff weight of 3.5 tons is adequate, and also the empty weight of 1.4 tons. The fuel weight that the aircraft uses on its mission profile is 500 kilograms, which means that the payload weight is around 1.6 tons. And this is the parameters for matching chart. The takeoff distance is 600 meters. The top 23 is 268.91. The CL max on takeoff is 1.7. The takeoff, the omega is 1. The landing distance is 650 meters. The stall speed is 64 knots. The air density during landing is at least at sea level is 0.002377 slug per feet cubic. The CL max on landing is 2.3. The cruise speed is 250 kilometers per hour. The performance index is 0.9. The air density, the omega at 12,000 feet is 0.2546. The swell speed is 60 knots. The aspect ratio of the wing is 8, and the Oswald efficiency factor is 0.8. And then Fahmi can continue.
All right, thank you, Bayu. So this is the result of our constructed matching chart. Based on the region that can comply the requirement, our design point will be wing loading 1300 Newton per meter square and power loading 10 kilogram per kilowatt. This matching chart consists of takeoff constraint, landing, cruise speed, stall speed, and rate of climb. And also we input the design point of our competitors in the matching chart. Next, please. These are some design parameters that we can obtain based on the matching chart estimation. We have the power loading and wing loading, CL max takeoff and CL max landing, and we can obtain the wing reference area and the engine power installed. We will discuss in the next slide, please. Based on our design power loading and maximum takeoff weight, we should have engine power requirement of 350 kilowatt. And our engine choice is Hawk E330GGT by AC Aero USA with 500 horsepower or equal to 373 kilowatt. The weight is 154 kilogram, and we will have 4 blades with 2 meter of proper diameter. Next, please. These are some specification of Hawk E330, and the dimension will not exceed 72 centimeter in length, height, and weight. Next, please. And then the next one is our design wing loading. Based on our design wing loading and maximum takeoff weight, we should have wing area of 27 meters square with aspect ratio of 8, wingspan 14 meter, and the root chord is around 2 meters. Next, please. And for the next one will be presented by Kerry. Thank you.
Okay, thank you, Fahmi. So now we go to the fuselage. For the fuselage cross section, our width will be 1.8 meters with corner radius 0.35 meters and clean cross section area 2.5 meters square. Our cargo will have a length. Our cargo room will have a length of 4 meters with volume of 10 meter cubic, and our nose length will be 2.9 meters. Empennage length will be 4.6 meter, and the total of fuselage length will be 12 meter. Next, please. And for the tail, for the horizontal tail, we'll have 5.2 meter the position, and the area will be 4.8 meter square, and the coefficient will be 0.5. For the vertical one, it will be positioned at 5.6 meters with area 2.85 meters square and coefficient of 0.05. Next, please. And this is our landing gear. We determined that our maximum load of the nose landing gear will be 20% of our takeoff weight, and we know that our center of gravity is 0.44 meters. Therefore, we can find the position of our nose landing gear and our main landing gear, which is 1.4 for the nose one and 4.95 for the main landing gear. Next, please. And this is our 2D model. We designed this using OpenVSP, and this is our 3D, our 3-view drawing. Thank you.